Welcome everyone to today's lunch and learn, and especially this lunch with a transistor. It is a twist. So we would be discussing and briefly going through the literature as well, where we will see how AI is rewriting the device design, especially like transistor, which is coming from the transferring the resistor and as a working as a switch. So my name is Chandrabhan Kushwah, and I'm really excited to take you through this blend of advanced semiconductor technology and cutting edge AI applications. Because we have seen a lot of AI application in different fields, and we are trying to get uh, that application into the electronic. Especially in my case, I'm working as a pillar two researcher here at April AI Hub at University of Edinburgh. So I would be focusing on the device design, especially MOSFET semiconductor devices, HEMT as well. So whether you are coming from an electronics background or computer science, or just curious about what the field is going next, there is something for everyone today. So let's move on to another slide where I can discuss about the today's agenda. Here is our menu, especially if we are taking lunch today. So this is the menu. Sorry for that. There is no such food in terms of like physically fulfilling atomy. Although you might have your own. I would love to provide you from my side, but unfortunately I cannot at this point of time. Anyway, so this is the our menu. First, we will talk about how AI has become important in transistor and device design, from where it came and what's the application we can have in the device design. Then we will look at some of the most advanced architectures, just like FinFETs, uh, gate-all-around FinFETs, and beyond as well. After that, we will explore exactly where AI fits in the form of device and device design and simulation. And I will walk through real-world use cases like TCAD acceleration and structure optimization and inverse design as well. So first question comes in my mind, that why AI in device design? So as we have seen, the AI is transforming the landscape of many different applications, economically challenges, and that's also where AI is everywhere. And how can we harness that power into that electronics, especially in the device design? So the key challenges and the complexity of these devices like transistors, and the complexity of their design and their long development cycles and high computational cost because of the simulation and processing, and also like fabrication cost as well. So these are the challenges where AI can be beneficial for us. So we can utilize this power into these complexity and challenges, and and especially like traditional methods rely heavily on manual iterations and physical intuitions, which can be slow and inefficient, because the scaling and the need of the hardware, which is very important for AI to deliver the task which we would like to have. So that's a difficulty here in the traditional methods. So AI allow us to automate these design tasks, predict performance design tasks, and high accuracy, and explore massive design space in the fraction of time, because it's a good idea to have a task dedicated for the AI, and that can do for us, and that will be faster than the conventional design approach. So not only accelerates the innovation, but also democratize the design process, enabling faster prototype and more robust solutions. Because the space which we cannot find from the manual approach, it can be possible that we can have the AI in tool with us, and we can find those solutions. And the next, if we see, we will see that overview of the history of next generation transistors, because we have to first understand what the transistor is briefly, and then how it came from the history to now, and what are the challenges which we are facing with the transistors. so that we can understand what is happening. So to understand where we are headed, it's important to reflect how far we have come. Transistor technology has evolved rapidly from the early days of planar MOSFETs to the current design of the MOSFET that's called FinFETs, and also having with them like gate-all-around MOSFETs. They are a type of FinFETs, but they are going forward into the design scale, and also called nanosheet transistors. So each generation has pushed the boundaries of scaling, power efficiency, and performance. So as we enter the era of, let's say, sub 5 nanometer to 3 nanometer nodes. So these are the technology node where we fabricate the MOSFETs, and the 3D integration, the complexity increases exponentially. So this is where general approaches in it's difficult. So including AI become essential to managing and designing such advanced architecture. We will see how this architecture looks like in the incoming slides. And so we will also discuss about some and see some use cases from the literature where we can see what is the importance of the simulation time. So that will come from the TCAT, because in technology and advancement, we need to utilize those TCAT tools, um, where we design a MOSFET and simulate it, and that takes a lot of time, because in case of we are going from the 2D devices to 3D devices, it's very challenging to simulate those devices. So AI is finding application across the entire device design pipeline. In TCAT simulation, it helps reducing the number of simulation, as I mentioned, and needed by learning from past results. In material selection process as well and optimization, it can also predict outcomes without exhaustive testing, because we model uh, those simulations as well. Most impressively, in direct device design, AI can propose novel structures. So that's very interesting, because as a device engineer, I would love to have a device which I would like, which is specifically for some parameters. I can find a device without going into the simulation and the fabrication. So it is possible, because we can train our models, AI models, in such a way that from the past data set we can have the new devices from there. So these use cases highlight AI potential, not just as a tool, but as a co-designer in modern semiconductor innovation. Now we will see that how and from where AI has started. So let's take a look at the historical journey of artificial intelligence. Sorry. So AI began its conceptual journey in around 1956 at Dartmouth conference, where the term was officially coined, as I could see from the literature. So early optimism led to project like ELIZA, the first chatbot, but technologically constrained. Soon it was ushered in the first AI winter. The next one, in 1970, brought a resurgence with expert systems, but again, enthusiasm wanted won in the 1990 due to underwhelming results and scalability issues. So leading into the second AI winter, was going through nicely. From the late 1990s onwards, AI experienced a rebirth. The landmark achievement like IBM's Deep Blue beating Gary Kasparov, and later Watson winning Jeopardy. So signal growing capabilities of the AI systems. Then the 2000 marked the deep learning revolution. So that was a key point from where we see the many applications of the AI, where pattern recognition, massive data processing, and computational power converged. So by 2016, AI had made profound strides, exemplified by AlphaGo's victory over a world Go champion. Now, today, we stand in an era where AI is deeply embedded in solving specific real world problems, especially driven by the innovation in machine learning, data science, and of course, neural networks. So this was the brief history about the how and what the path of the AI from where we came. So we will see the transistor history as well from from where the transistor came. So the evolution of electronics is typically marked by three pivotal device innovations. First is very old. It is a vacuum tube, and then the bipolar transistor came into the picture, and the metal oxide semiconductor as well. While the vacuum tube and BGT played significant role in laying the groundwork. For instance, here, if we see this is the BGT transistor around 1948. Uh, so playing significant this BJT playing the significant role in laying the groundwork for the modern computing. It was the advent of the MOSFET, especially in the form of CMOS design, which is here, uh, CMOS technology, that truly catalyzed the rapid growth of information technology over the past 60 years, from 1926 to now, 2022 or 25. This transformation has positioned IT as a central driver of today's technological society. A key advantage of MOSFET in advanced in very large scale integration is lies in the scalability, which has consistently improved from the time when it was invented. So which is a main factor or key factor of the performance, such as cost, speed, and the power efficiency. And the inherent characteristic of CMOS circuit, notably the use of both PMOS and NMOS MOSFETs and their field effect operation, allow for extremely low leakage, because when PMOS is on, the NMOS is off, and when NMOS is on, then PMOS is off, and there is no such high leakage current, very tiny leakage current. So this was the very crucial circuit design, basic template for the big architectures. So this made an ideal situation for energy sensitive applications. If we see closely that the MOSFET idea, FET idea, was invented, coined very early, but it took a lot of time, and that was because of the early technical hurdle was related to the silicon dioxide interface trap. And once this was resolved, the CMOS technology rapidly surpassed bipolar transistors. If we see from there, very few applications of BJTs. Otherwise, the MOSFET has been a main driver of the technology. So, and it became the backbone of the digital and whole VLSI era. Over the last 50 years, CMOS has dominated the digital landscape, and also progressive technology nodes is smaller than 10 nanometer, and we are approaching towards the 1 nanometer and beyond that as well. We will also see some example that how far we have come and how far we are going to. So yeah, this is very interesting, and to see how challenging it is, and that's the place where the AI is going to help us to go further into the scaling domain. So however, this scaling journey has faced persistent difficulties, particularly short channel effects, because of the channel length is so tiny. I'm talking about the 7 nanometer is going through below the range of around 1 micrometer range. And so the gate device, if we are going to reduce down the gate length in the 1 micrometer or lower than that, so the short channel effects, so it is because of the channel is so short, it is called short channel effects. It's difficult to manage, and they come into picture after this range. So earlier effort to manage these effects focused on physical scaling, gate oxide layer, and tuning doping profile in the transistors, source, drain, and channel region. But in the 21st century, attention has shifted to advanced materials and novel structures as well, such as silicon channel, high K metal gate, silicon on insulator platforms. And the very interesting one is FinFET architectures to address the scaling challenges. So these all the solutions were came into the picture around the 21st century, so that we can cope up with the scaling challenges. So according to, it's very interesting to see that according to the latest international roadmap for device and systems, further scaling beyond the 5 nanometer threshold may plateau a gate length of 40 nanometer for low power and 12 nanometer for high performance applications, potentially hindering future progress. So this is very challenging task. So this perspective therefore aim to spotlight the most viable sub 5 nanometer logic technology and delineate the critical research directions needed, helping to streamline and strengthen ongoing efforts across the field. So this was the very interesting journey from vacuum tube to BJT and the MOSFETs, and from the invention of the MOSFET, it's just continued for past 60 years is still going on with the different structure and optimization. So let's see how the transistor count and what the transistor has been a main driver of our systems, especially computers and hardware. So in this chart, this is especially for came from the Moore's law, which is actually Moore's law is a prediction where he predict that the number of transistors on integrated circuit would double roughly in every 2 years. So from the early days of Intel, there was an Intel 4004 processor in 1971 with about only 2,300 transistors. To today's state-of-art processor, this exponential growth has powered decade of innovation. And if we see an example of the last year's advancement in technology, NVIDIA has showcased B100 GPU and that is an example of pushing the boundaries. It packs around 200 billion transistors achieved by combining two reticle limits die, and this was happened first time in the history that the two reticle was combined together. And a total of 208 billion transistors, and each reticle has 104 billion transistors, and these are seamlessly joined to behave as a single massive monolithic IC and fabricated. And this was very interesting to see that this was fabricated using TSMC's 4 nanometer FinFET process. So the FinFET was the key component as a transistor in this architecture. So this device exemplifies the engineering complexity and scale required to continue Moore's trajectory. However, Moore's law is reaching its physical and economic limits because it's challenging to cope up with that one and continue this with the fabrication as well. So as transistor approach atomic scale, quantum tunneling, increased heat dissipation, and the extreme cost of fabrication challenge continued scaling. Notably, moving from 10 nanometer to 7 nanometer monodes now yield diminishing returns in performance, energy efficiency, and especially in cost per transistor. But in parallel, we must consider the end of Dennard scaling as well. He proposed in 1974. Dennard scaling suggested that the transistor shrink, the power density shrink, but the power density remains constant because both voltage and current scale down. This allowed chips to become faster without increasing power consumption, but by the mid 2000, this broke down, and leakage current, current and thermal bottlenecks, and inability to reduce voltage further mean that the power consumption started rising again, and even a transistor size shrank. Together, these shrink marks turning points. While Moore's law still drives progress, we are seeing a pivot towards new paradigms like chiplet architecture, 3D stacking, GA-FETs, and domain-specific accelerator as engineers and researchers seek alternative to the classical transistor scaling that we are going to see in the next slide. Here that the start of the first MOSFET structure, which is a planar, we call it planar structure. So this has been started. So there is a two MOSFET transistor, P-type and N-type, where there is a gate, a source and drain area. and the bulk. So when we apply the gate potential and create a potential difference between the drain and source, we can have a channel in between the source and drain region, and this is the gate. So this channel is formed, then the current can flow between the source and drain. So this is a basic function of the transistor. But because of scaling, that short channel effects came into the picture, as I mentioned. And to cope up with those short channel effects, we would like to have more control over this channel area. And how can we achieve that one? So we try to make this structure like 3D structure where the gate region, channel region has been extended vertically, and the gate was wrapped around to this region. That's why it is called fin, because it's structurally like a fin effect. Fin. So field effect transistor. And now we are moving to the gate all around, because if we closely see that these fins are wrapped around from the silicon. So that's why it is gate all around MOSFET, and there are the sheets. So these are nanotubes and these are the sheets. So these are the structures they are going forward in the scaling. Only that's the reason that we are be able to make such kind of devices, which we talked about in the previous slide. So especially this slide captured the architecture evolution of transistor as we push into advanced technology node beyond FinFET as well. On the top left, I mentioned there's a CMOS structure, and uh, and other than that, we are moving from planar to gate-all-around MOSFETs. As we move forward, the image of the middle section, which we discussed, that we are utilizing the GFETs in the future technologies. So as in FinFET, the gate wrap around the vertical fin improved the electrostatic control compared to the planar MOSFETs. Uh, and then we also shifted to the gate-all-around FETs. So the nano ribbons, and this is called the nano ribbons and nano sheets. If we see closely, that the performance has been increased from if we are going to use the FinFET gate-all-around structure to the nano sheets or nano ribbons. So, and if we see closely, that the FinFET has also been utilized for the different structures. On the right side of a set of 3D illustrations explores vertical stacking configuration, like vertical nanowires, vertical nanosheets, and vertical 2D sheets. These concepts aim to maximize the channel density while minimizing the footprints of the device, so that we can accommodate more devices into the same silicon area. So this is a critical for the continuing Moore's law as we approach the physical limits of the traditional scaling. Overall, this visual showcase how device engineering is now much about 3D architecture and material innovation as it about the shrinking dimensions. We will also see the new kind of devices can emerge from the combination of different material and the structures. So although MOSFET have powered decade of computing innovations, their operation mechanism are starting to show fundamental limits as we scale down device sizes. We are not uh, s- uh, seeing proportional improvements in power efficiency or energy consumption. This has led researcher to explore alternate transistors concepts, often referred as a uh, beyond MOSFET technologies, to overcome this bottleneck. To guide this exploration, it's useful to go back to the basic of what a transistor is. The word itself combines the trans and the resistor, so referring to the conductive channel, as I mentioned in the previous slide, where we are going to increase the conductivity of the channel so that it can transfer the resistor from high to low. So referring that transistor and resistor combination, it is essential we are manipulating charge carrier, the resistors, using a control mechanism that is trans. In traditional MOSFET, this modulation comes from an electric field applied through a gate capacitor, while in BJTs it is controlled through through a PN junction. So now researchers are looking at re-engineering this control mechanism, promising innovations include negative capacitance FETs, mm, and negative capacitance FETs, and suppose suspended gate FETs as well, and mod gated FETs. These devices experiment with new physics, like using ferroelectrics materials to achieve a negative gate capacitance, or employing nano electromechanical or phase change switches to rapidly boost current flow. So these changes enable steeper switching characteristic, which is a key for the reducing power use. However, there is a trade-off. And that is these new mechanisms often introduce hysteresis and a kind of memory effect which limits the use in fast logic based computing, and still they show strong potential, especially in memory application and energy efficient circuits, especially tunneling FET TFETs, revisiting two aspects that which are very good at for the scaling technologies. So there are these challenges where how can we utilize these different materials and the device structures. So let's move on to the next slide where we will see that how AI can provide the solution of these. So till now we have seen that the how AI has evolved, and also like transistors, how they are coming from the vacuum to the gate-all-around structures, and what are the challenges in the design of those transistors and scaling to a high level of density. And also like going forward to get a design from the different materials and different devices structures. So how can AI give a solution in here? So because when we design a device, it's very important to check its characteristics. So to check those characteristics, we have to utilize the simulation or use the simulation tools to check it, and that's very important to increase that simulation time, because nowadays what is happening when you are um, simulating a 3D device, it's very difficult to get at a characteristic within an hour. It takes more than an hour, sometimes it takes days. It depends upon the meshing and other conditions as well. So where does AI come in? So I think it helps tackle the four big pain points, like faster simulation. First is that. So in fast simulation, one of the key advancement, we are focusing on the significantly accelerating simulations. And the traditional physics-based simulation can be computationally expensive because these are based on the equations, partial differential equation, device physics equations, and they are very time consuming. So by integrating more efficient numerical methods for leveraging machine learning models, we can drastically reduce simulation time, enabling quicker design iteration and faster decision making in real world application. So this is very interesting to see that if we can get the higher simulation speed. So, and second one could be like high dimensional optimization, because AI can provide an optimized device where you can have the output characteristics that depends upon the previous history of the device characters. So in these kind of complex system, there are often hundreds of parameters to tune. This is what we refer to as a high dimensional optimization. So standard optimization technique struggles with such a complexity. To overcome this, we use advanced algorithms such as Bayesian optimization, evolutionary strategies, or dimensionality reduction techniques, which help us navigate these massive design spaces effectively, and identify optimal solution and much more efficiently, as AI could help in that. And also like learning based device prediction. So instead of simulating or manually modeling every new device from scratch, we can now use learning based approaches to predict device performance. By training model on the existing data, we can enable rapid and accurate prediction of new designs. This not only saves time but also opens up opportunities for real-time feedback and automated design generation. That also revolutionize how we approach device development. So I think the AI could be very helpful in this kind of situations and provide some solutions for the device design. So let's see some case study where we can see uh, how the structure has in the research they have designed and developed kind of utilize the AI uh, for the device design. So here we will see the machine learning model can be trained to predict the outcome of the device design in very quick manner. And the design iteration speed can also be increased dramatically. So let's see how this has been done in this case. So the objective to accelerate semiconductor device simulation is by replacing the traditional bias ramping and with neural network predict initial solutions. So thereby reducing computation time without sacrificing accuracy. So core idea of this simulation is to solve complex computed nonlinear partial differential equation. Example, drift diffusion model using the Newton-Raphson method, which requires good initial guess. Normally, engineers use bias ramping and computing intermediate solutions to build up to the target condition, but this is the time consuming, I think, and this work, especially this work proposes training a convolutional and neural network to predict the electrostatic potential for a given device structure and target bias conditions, and effectively providing a high quality initial guess as well. So, so it handles variety of device structures, especially by incorporating physical parameters like channel length and oxide thickness, even on unstructured grids. So this was helpful. So CNN-based initial gas generator learns to predict electrostatic potential distribution directly from the device parameter and bias conditions. And the performance conditions show that this ML-based initial gas reduce the simulation time significantly compared to the conventional methods, while maintaining numerical stability as well. So the benefits is the obviously the it should be the drastically faster simulation and no need for the time-intensive bias ramping makes the device simulation more scalable and accessible in the large scale environments. So to construct a 2D image representation of the electrostatic potential, values are sampled at predefined grid. Uh, uh, Points across the device. If a sampling point doesn't align exactly with the mesh nodes, interpolation is used. Since the device uses an unstructured mesh with the regular elements, it's straightforward to interpolate the potential values within the element that contains the sampling locations. So choosing an appropriate sampling point is crucial because the device dimensions are very particularly with the gate length. Fixed sampling coordinates are impractical. Instead, sampling positions are defined as a function of gate length and position index. So, for example, in horizontal direction is shows that gate spans from the 44th point. Within vertical direction, junctions are source and drain are located around the 36 points. So the sampling points are concentrated near the junctions to ensure the details. And this method allows us a device instance within the design template to be represented on a standard 64 by 64 tensor grid, and that capturing the entire silicon region. Um, so note that this insulated region, such as gate oxide and nitride species, are excluded from this grid. So these regions exhibit relatively linear behavior and can be easily solved using a Laplace equations. So they are not necessary for the training data focused on modeling and nonlinear semiconductor behavior. Excuse me. So this outline the both workflow, both training and the inference, given the vast design space, 7 dimension in this case, including the 2 bias voltages, uh, and exhaustive sampling is infeasible. So instead, a diverse set of device configuration, it is randomly generated using a uniform distribution. The simulation output for each configuration is then mapped into the 2D matrix via the sampling method and treated as an image input for the neural network training. So during the inference, the trained neural network produces an estimated electrostatic potential image based on the given set of input parameters. This image then interpret this image interpolate back to the match, the original unstructured mesh. So the original unstructured mesh provide an accurate initial potential profile. This profile is used to initialize the simulation directly at the target bias point, eliminate a need of intermediate bias stamping. So that's the reason behind that we can get the high performance. So this shows that the ML-based initial gas reduction simulation time significantly compared to the conventional methods, while maintaining the numerical stability as well. So this is a very interesting case that where we can see that how the simulation time has been reduced to around 5x time uh, without using this complex design. So we will also see one more case where we can have the device structure can be found with the neural network model. So let's see how does it work. So here we were talking about the FinFET and other structure. So this is the very simple case of pin structure where we can see how the pin structure can be optimized for the multi-objective tuning and also like automatic exploration for the different configurations. So how this work present a machine learning framework that integrates uh, two autoencoders with a linear regulation model to enhance the accuracy and the robustness of the technology computer-aided design or TCAD. Also, like it has augmented machine learning, especially for identifying the semiconductor structure variation. So and enabling the inverse design as well. So from the parameters, we can have the device design as well without relying on domain specific heuristics. So we can train the model and then we will reduce down the expertise knowledge of the domain. So TCAD augmented machine leverages. So we simulate the device in the TCAD simulator, also get the data, and then we train the model, and then we can find the optimized value as well as inverse design or the device structure. So this simulation data to supplement the sparse experimental data sets, enabling model training under realistic conditions. So we simulate the device and then we generate the data to find out the condition which can be realistic for the device. In this study, the method is demonstrated using a pin diode, where the goal is to infer variation in the layers um, uh, and the thickness from the given current voltage IV characteristics. While TCAD simulations can readily incorporate such variations for training data generation, conventional ML models tend to overfit sometimes, especially when unseen physical factors, hidden variables affect the IV response in experimental scenarios. To address this, the proposed model architecture employs autoencoders to extract the latent features that help generalize beyond the training distribution to test its effectiveness, and a second set of ticket simulation as well. So the augmented with doping concentration variability was to emulate the experimental uncertainties. So these results shows that the proposed approach significantly outperformed the conventional models, achieving greater accuracy as well, predicting the structure parameter, and the model proves effectively going for the inverse design as well. So to evaluate the effectiveness of this, the proposed model auto combined, this was employed in a reverse engineering task. So the custom IV curve was manually drawn. So this is the manually drawn curve. This blue line is a hand-drawn curve, and simulating scenario in which the device designer sketches the target IV characteristics for an integration or process engineer, while ensuring it remains within the bound of the current fabrication capabilities. This hand-drawn curve was discretized and input into the model, uh, or as auto combined into the model to determine the corresponding layer thickness, different thickness of the pin diode. So P thickness of P region, thickness of N region, and thickness of internal region, intrinsic region. So model returned the values which is very close to the hand-drawn values. So this structure was simulated using the TCAD and compared to the original hand-drawn curve. The result demonstrated the simulator IV closely replicate the uh, reverse leakage characteristics of the input curve. So during differing by only about a factor of 4 across much of the negative voltage range. This level of accuracy is very notable, especially since the model was trained on the data set, which is not that high order. So it is only 508 points of that. So that spans of 4 order of magnitude in the leakage current. So in the forward bias region, the model also aligned well with hand-on curve up to 1.5 volt for VA greater than 1.5 volt. So, and deviations occurs, though this is expected because um, as the shape of the hand-on curve is in this region does not physically align with the standard diode behavior. The model instead prioritize a smooth transition around the built-in potential, which is a more realistic outcome. This intelligent trade-off reflect a deeper understanding of the device physics. That is an insight that would be difficult for a human expert to naive model to replicate, as they might otherwise match the curve at 2 volt, and so the cost of physical plausibility. So for comparison, reverse engineering was also attempted using the other models and returned nonsensical results, but they are not shown here. So this confirmed that simply incorporating more training data, even in the include realistic variation, is sufficient for generalizing unseen patterns, such as those present in the hand-drawn curve. So ultimately, model auto-encoder combined proves that to be more robust and capable of learning the underlying device physics, making it a strong candidate for TCAD augmented machine learning workflows in the semiconductor design. So we could see that how the machine learning can be useful for designing a device from the characteristics. Even if you draw the hand on curve, even if we go for the different scenarios, then we can also tell the designer that whatever you have given us, it's not in the range, because if he's going to draw this one, then there would be a different material to be utilized for this device. If it's going there, then the different material to be utilized. So we can also include the stochastic variability into that, and then we can also get the inverse design out of this process. So this was very interesting to see how the AI can help into the design of the device. That's a new, and not just one device. There will be multiple devices we can achieve from there. So Now, this slide take me to the my final wrap up and reflection. Where as we wrap up, let's reflect on the key messages that, from my perspective, AI isn't here to replace designers, because even if you go for the automation of every aspects of that, there would be a very crucial element of the designer, which has experience in the device physics and the experience of the process and the fabrication as well. So it's AI here to empower that role, and it will work as a tool. The role of the human expert is still very crucial, but now augmented by intelligent tool that handle the repetitive computational heavy work. This gives us more room for to focus on the creativity, intuition, and innovation. So, this is a very smart tool would be there. So AI can work as a with the AI driven tool. We are seeing a fundamental shift. Designers are not just faster to develop, but they are often better optimized and more innovative. So AI helps uncover design options we might not have considered, pushing the boundaries of what's possible. It's not just about speed; it's about smarter and more efficient engineering. So, what from my perspective, what the transfer twist will you explore next? So, I think I would be going. In my case, I would be going for FinFET and inverse design. And but in chaos, and I want to leave you with a question: what transistor twist will you explore next? Whether it's a novel architecture, a material breakthrough, or an AI-led design approach. The future of device design is wide open. With the right tool and mindset, you have the power to shape the next generation of semiconductor. And here in April Hub, I'm building a AI tool that can develop a device, or give you the device as I mentioned in the previous slide, so that I'm working on the inverse design, where we can find out the device with the higher simulation speed. So we will simulate the design first and generate the data, which is very crucial, because in case of device design, it's very difficult to get the data from the open source possibilities, and also from the industry. So it's difficult. So I'm focusing on the generating the data from the simulation, and then extracting the data from the literature to test my system that is built on the simulated data. So that's the next thing I will be going for, and with the FinFET and hemp structures. So what's about yours? So thank you for this talk. Thank you for listening patiently.